Are you able to
Yes.
see my power? Okay.
Yes, sir.
Okay. Okay. If you recall what we have discussed so far, we've basically in the first lecture, we've gone over some of the fundamentals of seismology theory, essentially the basic equations, and then we derived wave equation in different forms. Wave equations, we looked at full anisotropy and heterogeneity. We looked at VTI. We looked at elastic. We looked at viscoelastic, and then we looked at acoustic, and then we looked at constant rho or constant density acoustic. So essentially what we have is a partial set differential equation, which you can write as Lu equals F, where this L is the differential operator, and then we've seen different forms of it. And for modeling, the fundamental problem is how do we solve it, right? So we can uh, we can take a couple of approaches to solving this. One would be to simplify the model, and the other would be to basically uh, get asymptotic solution where you can keep the model as complex as you want, of course, within certain limitations. And of course, the third option was to use a brute force numerical method, where we can keep the model complexity however we want, but then try to come up with a numerical approach to solving partial differential equation. And so far we've looked at two approaches. One was to simplify the model in the sense that we said that our model can be 1D in the sense that the velocities and densities and all other elastic parameters, they vary only as a function of depth. And for this kind of a model, uh, we can either use a straight wave plane wave solution, which is our normal incidence plane wave solution, which is our post-stack solution. But when we actually try to solve for a point source, we use something called reflectivity method. And we've gone into details of that. And then the second approach we took was to see if we can get some approximate solution, an analytic solution, approximate analytic solution that is valid at high frequency. And that involves using approaches such as asymptotic array theory, which we went over quite a bit. And then in array theory, we identified two fundamental equations. One was your Eikenel equation that gives you travel time, and then the other is your transport equation that gives you amplitude. And then we also looked at a couple of variants, such as Kirchhoff method, and also we looked at bond series. And in bond series, what we did is we said that our velocity model V, I can, in general, which is a function of x, y, and z, I can represent this as some background velocity V plus some perturbation delta V. And this gives us some solution which is not necessarily, which is not exact, but it can be practical for many applications. And one big problem with this bond series type of approach is that your delta V over V must be very, very small. And the series that we use to represent full solution diverges. So you can only use a few terms. The first term is your, or zeroth order term is your standard bond approximation or bond scattering. Then we looked at a variant of this, which is a convergent bond series, where essentially we're using a damping term. Now, if you have any question, just unmute yourself and speak up.
So in the case of 1D, when we
Yes,
use point source, we call it 1.5D. Is it correct,
exactly.
sir?
Yeah,
Okay.
yeah, yeah. Okay, so today what we're going to first focus on is numerical method. And in numerical methods, we don't necessarily have to approximate the medium. The reason I'm saying not necessarily is because numerical methods also come with their own drawbacks. And in some cases, you may actually have to approximate the model, like in finite differences. Interfaces will be represented by some kind of a staircase model. And again, it depends on what frequency you are using. So let's look at the most popular method, which is the finite difference method, and it's used extensively in exploration seismology community and in all our industrial work, data processing work, we use finite difference methods. So again, what I will do is first go over the wave equation just to remind you what those equations look like, because only then we can put it in the context of how we can solve it using this finite difference approach. And you remember that in my previous lectures, I frequently talked about time domain and frequency domain approaches. And so we will look at both kinds of formulation, like both time domain and frequency domain formulation, and see how we can solve those using finite differences. And then in finite difference also, you have several categories, like we have standard grid, finite difference, and we also have something called staggered grid. And I'll discuss both of these. And one of the most important things that you need to remember is what kind of errors you can get in finite difference approximation. And I will talk about that. There's one other method which I'll briefly mention, which is called pseudospectral method. It's basically solved in Fourier domain. I will just have one slide on that. And of course, there are some finite element based methods which are also becoming slowly becoming popular. For example, in the academic earthquake seismology community, they use finite elements, but it's not so common in the exploration group. So I will try to connect that, but again briefly. So main focus is on finite difference methods. Okay, so we will always look into a first order system and a second order system of equations. So when I say first order and second order system, by that what I mean is if you go back to your fundamental equations of seismology, there was one equation which is basically Newton's law of motion, right? Divergence of tau plus F is equal to rho u double dot, right? And then there is there's Hooke's law, which is your C or tau, which is the stress, is given by C grad u, right? So you can either choose to solve these two systems what would mean that first you solve for maybe given displacement, solve for stress, and then given the stress, you can solve for the displacement. And the reason we're calling this first order is typically in a system like this, rather than using the acceleration term here, we use the particle velocity. So that would simply means the first derivative, and that would mean we have to actually put in a dot here as well. And if we did that, so then we can solve for the u dot and this time derivative, and you can also have this. So so this will be your first order system, because this involves first order derivative of both velocity and particle velocity and stress. Okay, so if this is u dot. Okay, so on the other hand, if you plug in the stress strain relationship into your equation of motion, that gives us a second order system. We just still keep it second order in displacement. So this is what it looks like for the acoustic case. For the acoustic case, this is your equation of this is uh, your pressure term, and I have actually included a time derivative, but this is essentially Hooke's law. Okay, and just that we have a time derivative on both left hand and right hand side. So rather than having a divergence of velocity displacement, I have a velocity, because on the left hand side I have a time derivative. So this one k is your compressibility, and rho is the density, and rho comes in here where I have rho del b del t is equal to this. So this is our Newton's law, and that's our Hooke's law. And when we plug this in here, I get this second order system. Okay, so this is second order derivative in time. Del 2p del t2 is this. Now, first thing that you notice is that if you want to solve this particular first order system, you have two field variables. One is your pressure P, and another is your particle velocity V. On the other hand, in a second order system, you are actually solving for only one field variable, which is P. So this may appear like an advantage. You may like to think that, okay, I need less memory, I need to propagate, one less variable, and which is true. But then it has been shown that this is not always the best system to use when you start to use things like staggered grid system. Now the same thing. Now you can also take this time domain equation and you convert it to frequency domain. All that you do is take a Fourier transform in time, and that gives you a new system. Here we have, this is your partial derivative. This is Laplacian, and this p hat is now a function of omega and the space variable x, y, z. On the other hand, p is simply a function of x and t, right? So the t is replaced by omega by simply taking a Fourier transform. Okay. Okay, and here I have not included viscoelasticity. It can be included, or viscosity, and it can be included, but that will just make the algebra a little bit messier. All right, so now we look at elastic wave equation. So in the elastic wave equation, this is our first order system. So in the first order system, these are your particle velocity component. Remember, this is in 2D, but 3D analog is very simple. So if you have velocity v, you can write this as vx, vy, and in 3D, there'll be a vz component also. But in 2D, I'm just keeping vx and vy just for demonstration purposes. And this sigma is now our stress, and lambda, mu, and so there are. So when you take a 2D wave equation here, I have three model parameters, lambda, mu, and rho. And then I have Vx Vz, I have sigma xx, tau xx, sigma zz, and sigma xz. So we need to have uh, three parameters for describing the model. And to compute the wave field, I need to basically propagate 1, 2, 3, 4, 5. So 5 variables, okay? Now in 3D, this becomes 9 because you have 3 components of velocity and 6 components of stress. So you can also plug this in, you can merge these two and come up with a second order system. And so in the frequency domain, if you look at that, in the second order system, what we have is this one here. Now it turns out that you can take this and you can actually write this in terms of a matrix equation. A omega u is equal to f hat. Now whenever I'm using hat, that means it's in Fourier domain. And this A comprises two matrices K and M. This K is called the stiffness matrix and M is called the mass matrix. Okay. And these are defined by the discretization method. So the very first thing that you do when you're using a numerical method is to discretize your model space. Okay. So in 1D, discretization was simple. These were all different layers. But when the medium is laterally varying, you have to define those velocities and displacement in grids. Okay, that is. Now, so what kind of grid do I use? Do I use rectangular grid? Do I use triangular grid? And this has been in discussion and debate for a long time. So for now, we will just look at we'll standard discretization in rectangular grid, but then we'll look at two different ways of solving it. Okay, so what is finite difference modeling? Now, finite difference method is a direct and straightforward approach to solving wave equation. And I can tell you the story when I was a grad student. What I worked on was more Kirchhoff and path integral formulation analytic solution. And my advisor, who was more of a mathematician and then a seismologist, he used to hate numerical methods like finite difference because he says that there is no math in finite difference. And finite difference methods basically don't require you to understand the physics of the problem, which is entirely true. But then it gives you a more complete solution. So remember, when we looked at ray theory, we looked at bond series, and we looked at reflectivity method. That required that we understand the wave propagation theory. The finite difference is a brute force approach. It's direct and straightforward, and it's anybody trying to talk? Okay. So the main features of this approach is that it uses basic equations. You don't need to transform and come up with a different form of wave equation like we did in reflectivity. We converted our partial differential equation to ordinary differential equation and so on. We need initial condition and some boundary condition, which I'll talk about then. So there is minimal analytic effort. You don't have to do any math to be able to do finite difference. So how does it work? Well, I'll come to that in a second, but sounds very attractive that I don't have to do any analytics and I don't have to do any math. I don't have to really get into nitty-gritty details of physics, which is a dangerous thing to do because at the end of the day, you have to be able to understand the physics. And but still, it seems like a very attractive feature. But then, in America, we say something that there is no free lunch. Whenever your office takes you to lunch, you should remember that there's something that they want to get in return. So there is no free lunch. So when I say that there's minimal analytic effort, it uses basic equation, we have some limitations. The limitation is the size. and complexity of the problem that you can solve by finite difference method. So when the model becomes very large, like 2D, 3D, when you become more parameters, and when you want to go to high frequency, FDM becomes very, very expensive. So we try to use GPU, multiple CPUs, and so on. Okay, so what is finite differencing? It's very simple. Everybody in this room is familiar with the Taylor series expansion, the very basic calculus. So you represent your function x, and you can say that at phi of x plus or minus delta x, I can expand it in Taylor series. This is phi x. Then we have del phi del x delta x. This is the second derivative of phi times del x squared, and then third derivative times del x cubed, and so on. And the minus sign corresponds to phi x minus delta x. So this is something that you have seen. Okay. And how does it help in solving our wave equation? Well, wave equation, after all, contains derivatives, right? Derivative with respect to time, derivative with respect to space coordinates. So let's look at some definitions of finite differencing. So let's say that I have a first order derivative I want to compute, is phi prime x. Typically, the notation that we use in seismology is a prime for space derivative and a dot for time derivatives. Just wanted to let you know because I'll be using those frequently. So del phi del x is 1 over delta x, phi x minus phi x minus delta x. So this is a linear approximation. The reason I'm saying this is that let's say that I have a function that looks like this. Okay, so this could be my x and this could be my phi x. And at any point I want to compute derivative, right? So let's say that I want to compute derivative at this point. So I take a function at a nearby point and take the difference and divide by the distance, right? That is our basic calculus. Remember, del f del x is equal to, or df dx in this case, is limit as delta x tends to 0, f of x plus delta x minus f of x by delta x. Everybody has seen that, right? So forward differencing is when you say that I'm looking at a point which is x here and x minus delta x is a point back, behind it. But you could also use a point ahead of it, and that would mean you get a difference like this. So these are both uh, equally valid, except for that it depends on what is the delta x. But then why should I just use this approximation? I can also use what is known as the second order derivative, where I take I could also, this is called central difference. So there are three different ways you can compute this. Let's say that I have this point x where I want to compute the derivative. So you have x minus delta x, and here I have x plus delta x. Okay. So I can compute the derivative here using the function value at x and x plus delta x. That will be my forward differencing. I can use x minus delta x and x. That will be my backward differencing. Also, I could use the function values at x minus delta x and x plus delta x and divide by 2 delta x. And that becomes my central difference. It's a very, very interesting approach. And the reason I say it's interesting is because one obvious question that comes in your mind is that then which one should I use? And it all depends on how much error is being introduced by these approximations and how is that error manifested in your wave equation simulation. So we also need to approximate our second derivative. And if you look at the Taylor series, if you just take these two, x plus delta x and x minus delta x here, this equation, one for x plus x plus delta x, another is for x minus delta x. If we add those and ignore higher order terms, you get a beautiful equation that basically means that to compute the second derivative at some point x, I definitely need function values at all 3 points, x minus delta x and x plus delta x. And this is how it goes. So this one, you put a weight of -2. This one, you put a weight of 1. And then you put a weight of 1 on this side also, and you divide by the x squared. And remember, I have ignored terms higher order than del x squared. Okay? You don't necessarily have to do that. This is called a second order approximation. You can have fourth order, eighth order, whatever. Nowadays, it's quite common to use eighth order finite differencing in finite difference simulation of wave equation. So, higher the order of the derivative, you expect to see more accurate solution. But again, with the caveat, we'll talk about in a second. But then also it involves more computation. So in general, you can write your finite difference operator as a series, and you can retain different orders. And here I'm showing you what the coefficients should be for different orders, half, 2 by 3, and so on and so forth. Okay. So this is for the first derivative. Similarly, you can write this for the second derivative. I remember when I was a graduate student, actually, I wrote a little Fortran program to compute the coefficients for different orders of derivatives. And you can actually play with different orders. And nowadays, you don't have to write any of these codes. They are all available in basically open source, and I'll talk about that at the end of this talk. So one of the things that we normally like to use is the standard grid. So what it means is that, let's say that I have, this is my grid, okay? So I say that I will define every state variable like pressure and velocity and particle velocity and wave velocity all at the same locations, okay? And this is called standard grid, which is fine. And so now let's look at what happens to my second order wave equation, which is the most commonly used one. So here, let's say that I'm using a standard grid representation. So I can represent my field and the velocity. It's a pressure is what we're computing, and I'm going to xi, yj, and tk, right? And when you discretize it, it's not a continuous function anymore. So at each location, you have to define a coordinate system where we are computing these variables. So x and y. So in this notation here, I'm using I for x, j for y, and n, not k, and n for time. Okay. So the second order finite difference, you can compute this as, this is Laplacian. So so when I say del square p, this basically means del x squared p plus del z squared p. So I need to have finite difference approximations for each one of these. So I can write this del x squared p as p x minus 1 minus 2 times p x plus p x plus 1 divided by del x squared, right? Now here, if I write it in discretized form, then this becomes your ij, and I'm writing the time derivative, time index as n as a suffix. So this is the second derivative operator for x variable. This is the second derivative operator for the z variable. But we also need to discretize our time variable, derivative of the time with respect to time. I'm sorry, as the same variable p, but derivative with respect to time. So now I have the derivative with respect to time. So I can write this as p. I can say t minus 1 plus minus 2 pt plus pt plus 1 divided by delta t squared, right? That's in my left hand side. So what I can do is I rearrange those in such a way that this is your at n plus 1 time step or t plus 1 time step. And on the right hand side, I have at n time step, this is at n plus 1 time step, this is at n time step, this is at n minus 1 time step. And this I already explained to you, and this is your velocity and other things. Cij is your slowness in this case, and ij, basically I and j indices for x and y. So the velocity is also defined at these grid locations, and it's independent of time. Okay. So this is actually the equation that we have after finite differencing of the standard constant density acoustic wave equation. So what is that telling you? And why do I have this form? The reason I have this form is that this equation is letting you compute your pressure wave field at a future time n plus 1 given your wave field at n and n minus 1. So let's say that I have, this is my spatial grid in 2D, and that's my time, right? So what I'm saying is that if I know the time, wave field at time, say t equal to 0 and t equal to delta t, I can actually compute the wave field as t. So you start at t equal to 0 and t equal to delta t. You assume that I know what those wave fields are, and it comes from your initial condition. And this is telling you that I can now compute at t equal to 2 delta t, right? So once we have that, then this basically becomes your current time snapshot. And I already have this t equals delta t, that becomes my past time snapshot. So I guess go to the, now I can compute the future time step. So we have past snapshot, then we have current snapshot, and from there I'm computing future snapshots. So in the next step, your current becomes past and future becomes current. Okay, and then you go on marching it, and this is called time marching. This is explicit time marching. And at each time step, you are actually computing the wave field at every grid location. And that's how you can actually see how the wave fronts are propagating in time. So this is a basic code algorithm, and I'm sure you guys can code it in 5 minutes. So this is, you start with your initial condition, tells you what the source is. I'll tell you how to inject the source. Then you evaluate the Laplacian, add the source term, you advance in time, and this is something that I'll talk about a little bit later. Apply some kind of boundary conditions. You want to record your receivers, you can, and then you can cycles to your storage. This is the part where your Pn plus 1 becomes Pn, and Pn becomes Pn minus 1, and then you repeat this loop. At each step, you are actually adding the contribution from the source. Okay, so this is the explicit time marching. Okay, this is called explicit time marching, and that is the heart of all finite difference calculations. So, in case of source, what you have is source is generally located at one grid location, which is your source location, and we have a source time function, which is probably something like this. And this is the part that you need to add at every time step, because this is also plotted as a function of time, right? So this has got delta t, 2 delta t, 3 delta t, and so on. As we march through our wave equation at different time steps, at each time step we are just adding the contribution of this. Okay. So this is the schematic of a finite difference model setup. In 2D, 3D is essentially the same. So let's say that this is the blue box. This is where I have the velocity model, and this is your source location. And you can see that I have put a boundary or a zone around the true model. And I'll tell you why I'm doing that. Because, well, the very first thing you do is that let's say that you're propagating your waves. So what happens when you reach the boundary here? And this is an artificial boundary that we are creating for simulation purposes. In real Earth, we don't have any such boundaries. So the waves basically simply propagate away. But in this case, what will happen is that because of these artificial boundaries, the waves will start to essentially get reflected from the boundaries, and it's going to contaminate your wave field calculation. To avoid that, we need to do some special treatments, and that is what we call absorbing boundaries, and I'll explain to you different methods for doing that. Okay, so you can then see how the wavefronts will propagate as a function of time, and then it will populate the entire model, and then it will get bounced from different boundaries, and then it will basically get reflected back. Now, one important thing that you notice here is that you can put receivers anywhere, because you're computing your wave field everywhere in the time marching algorithm. Typically, we have a set of receivers. So your job would be to then pick up the wave field and store it separately. Okay. And then generate synthetic seismograms from there. Okay. Any questions so far? Yes, they're awfully silent. That's okay. Okay, so here I just wanted to show you in a standard grid how the in 2D, how the grids are placed and how many grids you need for computing the wave field. So this is your second order. So in second order time marching, your stencil looks like this. So you want to update here and you have the wave field around there. In the fourth order, you need to have 9 points. So this is what the stencils look like. So this is your rectangular stencils. But there are other kinds of stencils that may actually be numerically more accurate. And we have written some papers on that, although they are not the mainstream finite difference application. Okay. So here, your cost per step is of the order of nx times nz operations, and the memory is 2 times nx times nz, and DLR is the pn and pn minus 1. So here, at any time in memory, you have to have two snapshots for the current time and the past time. Okay, you can swap those after one time step, but you have to have enough memory to hold these two wave fields in memory. Okay, and that's not a trivial task, because when I was a grad student, it was very difficult to store all of that in the memory. But if you want to store those on disk and then you want to read those, that's a very slow process. Because reading from disk is much slower than, again, it depends on the kind of disk. Now we have some faster disk also, but it typically reading from memory is much faster than reading from the disk. So, which is quite a bit, which will slow down your algorithm quite a bit. Okay, so if you have fixed memory in your machine and you're running a big model, it may not tell you that you don't have sufficient memory. So what it'll do, it actually swaps, and then that slows it down quite a bit. So we had, when you're in a situation like this, you can just see how much CPU is being used, and you'll see that CPU is being used for say maybe 30-40%, and then it's still swapping. It's swapping in the sense that it has to fetch the data from some storage. So
Sir,
here is an, yes.
so is it the reason why we do wave field subsampling? While I was working with the code, uh, it it opted for wave field subsampling to fit into the RAM. Is
Yeah,
it the
so yeah,
same
we
thing? What
do.
you're explaining?
Yeah, sometimes we do that. Yeah,
Okay. Yeah.
especially in FWI. In FWI, you have to have not just two. You have to have all time stamps, all snapshots. Okay, because when you back propagate the wave field, I will talk about that probably next week. Uh, when you back propagate the wave field, then one of the things that you have to do is to cross correlate with the forward propagating wave field at every time step. Now, if they don't fit in the memory, that will really slow it down. Okay. Okay, so here is an example of a finite difference model setup. So here we have a velocity model. This is the EAG, or this is to be called EAEG that time. And this is your solid body, and these are the faults, and there's a continuous velocity field. So these interfaces, even though they look like real interfaces, but these are discretized. So what you have is something like that. Okay. Now, depending on the frequency that you are simulating the wave field with, these can give some dispersion kind of error. They can give diffractions. Okay. So this is the limitation of the way finite difference works. Okay. All right. So let's say that this is what it is, and then I can put a short somewhere and these places. And like I said, you can have your receivers anywhere, but I can choose for the synthetic experiment. I choose a receiver, let's say everywhere. And even though for marine experiment, the way it works is that if you have a shot, it tows an array. It basically it tows a streamer with hydrophones, and it actually pulls the streamer. So it's not always receivers everywhere on the surface, but this is how it actually stores it. And in 3D, we also have like 6 to 12 streamers nowadays. So let's say that I can put the source. Very important point. Every time you change the shot, you have to rerun the finite difference simulation. Okay. So if ns is the number of shots, you have to do ns number of finite difference simulation. Okay. So for these 4 shots, the streamer kind of geometry, this is what the seismograms look like. Now uh, this is very different from what you normally used to seeing, right? They're because this is laterally heterogeneous medium, you're seeing all these features. These are not all hyperbolic events. You can see these reflections, and they are all. This is all short gathers. Okay, so it is seeing all kinds of lateral heterogeneity. So you don't expect those to look like a simple, bunch of hyperboles like you expect for 1D model. Okay. So then another approach is staggered grid, and the reason I want to mention this is that this is a quite popular method, especially for elastic case. And in elastic case, what we do here is that the derivative of stresses and derivatives of velocities are not on the same grade. So what we do is we shift those by half a grid point, in the sense that you don't really shift it in your code. You actually use this kind of approach to define those that have grid locations. Essentially, you don't have to generate two separate set of grids, but you can use the same set of grids, but then use one for half a grid, one for the full grid. The only difference is that the properties, the velocities, particle velocity, I'm not the wave velocities and densities, they have to be interpolated to be able to do that. But that's a minor detail. So it does not, well, it does require quite a bit of memory, because you were trying to solve this in first order system, okay? And in second order system, we don't really need to do this. Not necessarily. Yeah, you don't need to do this. But in first order system, we do that. So, but then, you can ask me, like, in second order system, I'm actually propagating in elastic medium, I'm propagating my three displacements, right? Ux, Uy, and Uz. And I have, say in elastic case, I have lambda, mu, and rho. So essentially, I have six variables, right? And I have an x, and y, and nz, right? Now, if I do the staggered grid with the first order system, I have three displacements, or three particle velocities, and nine stresses, and six stress components. So total, I have 9 variables plus 3 parameters. So I have 12. So it is increasing the memory, indeed. But that is only true if you keep the same grid spacing, right? Now it turns out that you can actually achieve much higher accuracy with this staggered grid system for elastic case, with the same grid spacing, reducing this into half. Effectively, it's computing using a delta x by 2 and delta z by 2 kind of distance approximation. So even though it needs more variables, memory requirement may not be large, because your delta x, delta y, delta z can be coarser. And the reason is that there we can really show that it gives the same level of the numerical accuracy is about the same. The other thing is that in many of these simulations, we have the water layer, right? So this is the ocean layer water. And then we have the elastic medium. Now, you may think that if I set mu equal to 0, then I'm good. But in the second order system, it's not going to work. So you have to do an acoustic simulation here, and you have to do an elastic simulation, and then you have to match the boundaries. On the other hand, in staggered grid systems, the mu equal to 0 actually lets you put acoustic layers. Of course, for body waves, it actually works quite good, but there are some problems with capturing the right kind of surface waves, like swirlty waves and things like that. But those are some details. So overall, you can get a acoustic elastic medium using staggered grid method. So this is quite popular for elastic case. And the reason normally, if I was teaching this course maybe 10 years ago, I would not be talking about elastic case. But now it's very, very important, because everybody is now going to elastic FWI. So you have to understand how the elastic forward modeling works. So otherwise it's all finite differencing. The only thing is, the notationally, what we're using is the half derivative or half grid locations for some of these variables alternately. Okay, so each central difference is evaluated at its natural midpoint. So no averaging is needed. So this eliminates the odd even decoupling, but then we have to average some of the material properties there. Okay, which is a trivial task. So now if you look at acoustic Helmholtz equation, which is our frequency domain stuff, in frequency domain, there was a lot of discussion on frequency domain wavefield full waveform inversion, and initially that is what a lot of people, many people used it for applications to real data. Unfortunately, in 3D, it becomes very compute intensive. So essentially, what happens is if you take your wave equation and then you discretize it in frequency domain, which is wave equation meaning the Helmholtz equation, then you have a linear system, and that linear system basically has your a u equals f. A u is what you are solving for, and this a is a sparse. It's a complex. It's symmetric, but it's an indefinite matrix, meaning that first of all, to solve for u, you have to essentially apply an inverse of a, and getting that inverse is not trivial. In 2D, you can use LU decomposition, and which is most commonly used, but in 3D, it's not a very easy task. So this is what the structure of A looks like. There is this term which is essentially coming from the derivative, and this is where we're getting this frequency dependent term.
So, sir, there is some scope for mathematicians to work on the frequency domain.
Yeah, actually, I just submitted one paper on a new approach to doing frequency domain. So I
Okay,
can
great,
see,
sir.
yeah, I can send you a copy of that. Yeah, so this is something. If you can solve the 3D problem, 3D computation problem, that would be really a big winner. Okay.
Okay, sir.
Yeah, so this is what I was telling you. This is what it should look like, and this is what you have to solve. Okay, so in second order system, this is what it looks like. So yeah, here this shows you what the structure of this matrix A looks like for acoustic and elastic case. So this is essentially more like a block matrix kind of structure, diagonally dominant. And when you go to the elastic case, you can see you have some sub blocks for this. Okay, and this is quite easy to demonstrate if you just take a pen and pencil, take a pencil and paper, and you can just do the discretized system. You'll see that. So this is what the 3D one looks like. So this other method is called pseudospectral method, and here what is done is, let's say that I have this wave equation, which is my rho del t square p is equal to alpha squared del square p plus f, right? So this del is your del x squared p and del z squared p, right? Now remember your fundamentals, remember the basic properties of Fourier transform. When you have a function p and you transform it to p tilde, this is essentially your p tilde is equal to p e to the power I omega t dt, right? Now, if you have a del or I omega x kx dkx, sorry, I omega x dx, this is for special Fourier transform. So like I showed you earlier, when you have del Tp, that transforms to I omega p, right? And del T squared p will transform to I omega, so minus omega squared e tilde, right? So what is done here in finite differencing in pseudospectral domain is compute the derivative in Fourier domain. So what it means is that I can take a Fourier transform. This is a discrete Fourier transform for with respect to x and y coordinate. So this will give us ikx, and so the derivatives can be computed like FABUJ, do an FFT, and if you multiply by ikx, that gives you the derivative, and you can take an inverse Fourier transform that will give you this. So this involves one forward Fourier transform, one inverse Fourier transform, and that gives you this. And then you can discretize your time derivative in finite differences. Okay, but you can also do frequency wave number, which again is another approach. Okay, so now I'm going to talk about something called numerical dispersion. So what is numerical dispersion? Before I show that, let me show you this example. So here I'm propagating uh, elastic wave field. Okay. So what you see here is that as you go from left to right to the bottom, you can see a lot of ringing here. Okay. And it reduces from here to here. So what has changed? This is for a fixed frequency. So but by that what I mean is that in time domain, what is the frequency, maximum frequency? Okay. Now, what happens here in simple minded explanation is that if you have, say, grid points that are separated like this, now what we expect these to be more like a continuous distribution, right? But we're doing everything in discretized space. And the separation of this appears to be larger when you go to higher and higher frequency, right? When the frequency is very low, it thinks that these are all continuous. If it's lower, it's higher, then this appears, these will appear as discrete points. And because of that, you will start to see some ringing. This is very common in finite difference simulation. So people try to avoid this. They try to cut cost by reducing. They want to use high frequency, but the grid spacing they want to use is large, and then you start to see all of this error. This is called grid dispersion. And the way to look at this is simply take this wave field and apply. So essentially, put in a plane wave solution, and you can solve for this. And it turns out that you can actually see you can generate a relationship between the numerical velocity and the true velocity, and that is given by this equation. And based on that, we can come up with a grid sampling strategy. So it turns out that this delta x or delta z that we choose for discretization of the model, that depends on two factors. One is the velocity, another is the frequency. Why? Because this is essentially dictated by the wavelength, right? So v equals n times lambda. Everybody has seen that, right? Frequency. So this is basic acoustic wave theory that we have learned in high school, sound waves, right? So this is nothing but v equals n times lambda. So lambda comes from velocity and frequency. So if you did that, this gives number of wave points for minimum wavelength. So minimum wavelength will be C mean by and then F max. Okay. So delta x should be chosen such that it satisfies this criteria, and it all depends on the order of finite differencing. Okay. So there is a constant term which is different for a different order. So it is dictated by minimum velocity and maximum frequency. Okay. Now there's one other problem that we run into. Now, so this is your grid dispersion equation that I showed you earlier. So for uh, special order, second order, we need 8 to 10 grid points per wavelength. For third order, 3D, it's even more. If you go to fourth order or eighth order, basically the number of the grid spacing can be increased. But then yeah, so you can get the grid spacing, but then your stencil becomes longer, right? Remember, for second order, I have simply a 5-point stencil. For fourth order, I have more points here. So from 5 it goes to 9 and so on and so forth. So eighth order is even bigger. So you'll be doing more calculation per grid point, but then you can use a coarser grid. And this is the typical dispersion curve that we analyze. So this is telling you that if there was no dispersion, then your numerical velocity should be same as the true velocity. So it should be all equal to 1, right? Now with second order, as you increase the number of points per wavelength, that means as you decrease the frequency, this approaches that. For fourth order, it looks like this. And this is this is the main reason why in the industry, eighth order, sometimes they even use 16th order is a good choice. Okay, the other thing is stability. So in stability problem, what we have is that if we just substitute our solution, what you see is that this term is no longer with propagating wave. It's basically sine squared k, and then it turns out that your delta t. So first of all, I talked about how to choose delta x as dictated by grid dispersion. But then what about time stepping? It turns out that if you don't choose an optimal time stepping, delta t, then your solution grows and it becomes unstable. So you don't get your solution. So here the criteria is C delta t over delta x. So it's given by the product of C delta t over delta x. So delta t is dictated also by delta x. Okay. So these are kind of related. So as soon as you change your delta x, you have to change your delta t also. Okay. Main thing is to avoid numerical errors. And stability is the worst kind because it actually grows. The error grows so much that you'll see that nothing is happening. And earlier days, at least it will basically reach mission position and then it'll bomb. But what you can also see that its computer calculation is going on, but then you're not getting any significant update. Okay. Okay, so this is what I was showing you, grid dispersion. You can see that this is PSP, and you can see the dispersion here, ringing, and this is without dispersion. Okay. Okay, so I'd like to then at this point, let's take a short break and then I'll continue with this after the break. Okay.
Okay, sir.
Is that okay?
Yeah.
Okay, so let me start. Okay, can you see my screen now? The PowerPoint?
Yes, sir. Yeah.
Okay, so we talked about a couple of shortcomings with finite differences, and in fact, two. One was a grid dispersion, another is stability. And there is one other important consideration that we have to make, and that is the edge reflections. Like I told you earlier, in finite differencing, we are actually limiting our infinite domain to a finite domain. And because of that, the wave field actually gets reflected from the boundaries, and they contaminate the kind of reflections and wave fields that we're interested in. So to avoid that, we use something called absorbing boundaries. And the earliest work on observing boundary was reported by Clayton and Inquist. So what they did was to use one-way wave equation. So what it means is that when you take your wave field, it actually propagates in both ways. So can we actually devise or rewrite our wave equation in such a way that when it reaches the boundary, the waves actually don't propagate backward? Okay. Now, you may be, if you're familiar with the migration literature, one-way wave equation migration and things like that, that was pioneered by John Crabbe. Now, one of the applications of the one-way wave equation was also to use it in observing boundary condition. The idea here is that as soon as it hits the boundary, you switch from one-way to two-way to one-way wave propagation. Okay, and this one is reasonable approach, considering that this was done many years ago. And the limitation of this approach is that splitting your wave equation to one way can only be done approximately. And the implication of that is that these one-way wave propagators are valid only within certain angles. So, for example, if you're trying to propagate, use this wave equations, maybe they are valid for 15-degree propagation, 45-degree propagation, and so on. And beyond that, it will get reflected. So there was quite a, even though it kind of was able to get rid of some of the edge reflections, but there was still quite a bit of residual left. And then came this other method, which is basically simply very, very simple-minded approach. It was proposed by Kozlov and Sergian, those guys. It's very simple, very easy to understand. All that they said is that as soon as I reach my boundary, near that I will use some kind of I'll multiply the wave field with some tapering function. Okay. So typically they use exponential taper, and it basically decays from unit. Say here the weight is 1 going to 0. Okay. And once you did that, it actually does quite a bit of damping. Okay. And this is very easy to understand and very easy to implement. And then came something called perfectly matched layers, and this is the most commonly used nowadays. So what they're doing here is that they wrap the computational region by some kind of absorbing materials, and they compute decay factors in the PML formulations. And your wave equation needs to be modified. Okay, it's actually more complicated. So it adds a little bit to the computation cost, but it actually does work for many of the wave equation problems that people have used it. So here is an example of a wave field, a simply homogeneous medium. So here I have like a 2D domain, and there is no absorbing boundaries. So here, it does not touch the boundary, so it's all circular path. As soon as it hits the boundary, you can actually see the waves are basically getting reflected back. And after this is at different time steps. and you can actually see that this is totally contaminated with boundary reflections. And this is with our one-way propagator. And you can see, compare this with no absorbing boundaries, and you can see that this does damp, but there is still quite a bit of residual left. Okay. So this is one paper that we wrote a few years ago, not few years, probably more than 10 years ago, in geophysics. And this, Yang Lu was a postdoc with me, and we were working on this. And then I suggested to him to combine this damping with with the one-way propagator. So what we do here is that we put in a zone, and there what we do is we compute the wave field both with the two-way wave field and one-way wave field. And there is a weight term. So what we do is that we have large weight right here for the full wave field, but then when it goes to near the boundary, it basically goes to one way. Okay. So this is a weighted average of one way and the damping two way. And this is a very simple idea, but it actually works really well. Even in DeVito, people have implemented it. You will see that. So here is our example of our hybrid boundary conditions. So this is the same wave fields that I was talking about, no absorbing boundary. This is with our one way. And here we also had to play with the number of grid points in this particular damping zone. So it turns out that with 5, also we are getting pretty good absorption, but there is some residual. But when we increased it to 10, what we found is that it actually works like a sponge, and it has absorbed a lot of these things. And the advantage of doing this is that the algebra is very simple, and we don't have to use a complicated wave equation for applying this compared to PML. So here are some examples of short gather modeling. So here I have no observing boundary, and you can see all of these flexions coming in. If you try to run your finite difference code, you will see that this is quite common if you don't use it properly. This is our absorbing boundary. This is with clay. So if you have only one set of grid points at the boundary, that reduces to our one way. So here you can see there's quite a bit of edge reflections. This is less than without using absorbing boundary conditions. But there's quite a bit of residual here, but this is our new absorbing boundary conditions. Here you can see that it's pretty much eliminated. So we use that in not just standard finite difference, but also in pseudospectral. So same thing, you can see that with 10, it actually did a beautiful job observing these. And this is, so one way of actually avoiding absorbing and boundary reflections is to also increase the dimension of the model a lot. Because in that case, the edge reflections take a long time to come back and contaminate your, basically useful wave field. So here, what you're seeing is that if you use a very large model, that also helps you to get rid of these reflections, but this is computationally very expensive. But then with our new absorbing boundary condition equals 10, we are actually seeing very good absorptions. Similarly, for finite elements also, we have actually implemented this. This is no absorbing boundary conditions, and this is with our new hybrid with 10 layers. And you can see that this has also worked quite well. And these are the short gathers for finite elements. This is no absorbing boundary condition. This is for Clayton, and this is for our new approach. So here are your 3D examples in 3D block. When there is no absorbing boundaries, you can see a lot of reflections coming from the edges, and you cannot tell the difference between the real events that we're interested in and rather you cannot identify the real events because it's completely masked by edge reflections. This is with one-way propagator. This is slightly better, but still there's some residual. And this is with our new absorbing boundary condition. And then finally, in finite element, the approach is different. Rather than using a Taylor series, here we're representing it as a sum of basis functions. So I will skip that part. Just a couple of examples for anisotropic media. This we did in 3D for fully anisotropic media using the brute force 21 coefficients, three-dimensional model. And again, our equations were like this is our equation of motion, this is our Hooke's law, and this is our time derivative because we're using the first order system. And one thing that we realize is that we're using staggered grid, but then the grids had to be rotated. We call it rotated staggered grid because of the asymmetry, because of the symmetry conditions in finite difference in anisotropic media. So this is what the discretization looks like. You have the stresses, and these are the velocities. These are some of the details you'll find in our paper. So it turns out that standard staggered grid discretization can be used for isotropic TTI and orthorhombic symmetry. But for monoclinic and triclinic symmetry, we need to resort to something called rotated staggered grid. So here is an example of wave propagation in an HTI medium. And this is our velocity model. Unfortunately, I don't think I have the movie here. And this is our subsurface model. And this is your in TTI medium. And this shows you how in triclinic medium, this shows you your snapshots. It's a homogeneous, but it's a triclinic medium, 4.5 kilometer, 4.5 kilometer, 4.5 kilometers. And you can see these wavefronts are very, very complicated in triclinic medium. Okay, not that we have a lot of triclinic media for in seismic exploration purposes, but HTI, VTI, TTI can be all computed using this particular approach. So here is one example of 3D. So this is an isotropic subsurface. So you have these are the receivers, for example. This could be different sources. Both are isotropic, and if you look at some of these, look at the shard gather here in this plane. Looks like we have this duplication coming from this particular interface. And if you look at 3D anisotropic, where we have actually put in an HTI medium, and this is your isotropic medium. This has a set of vertical fractures with 5% crack density. These are dry fractures. And now I can show you some synthetics. This is your X component for the anisotropic media. This is Y component. So that's your direct wave. And this is the slower S wave polarized perpendicular to fractures. And this shows you faster S wave polarized parallel to fractures. And if you look at the move out, you can see that they are very different. And this is a typical shear wave splitting that you can expect when you have an anisotropic medium. Okay. And so this kind of tool is really, really useful to understand wave propagation, but to write a code, you probably don't have to understand the nitty-gritty details of wave theory. So one other thing I had my student do is to calibrate our finite difference with the reflectivity for fully anisotropic medium. And if you look at the comparison here, this is for simply layered medium. Red is finite difference and blue is reflectivity, and this is a super good match. If you look at Y component, but the same. Then you have the Z components. They're also matching really well. So finite difference is a general method. You can compute the wave fields everywhere in the medium. You can basically have any kind of geometry, and the model can be very complicated, barring the fact that you have to be worried about some of the numerical errors. And then it can also be written for anisotropic media, for attenuation, and for viscoelastic medium. All of these things are possible, just that you have to have enough computer budget to be able to run those. Of course, there are ways you can parallelize this. So here there are two basic packages that are like, not, I shouldn't say basic packages, two packages that are open source and are available for people to play with, which is really nice, because now you can write a lot of these codes and could run many of these models pretty easily. One is DeepWave, another is DeVito. And DeepWave is written, using machine learning libraries like PyTorch, and DeVito is essentially a PDE solver. I would say you can just write a PDE, and then it actually generates. You can use symbolic Python for doing a lot of these things in there. So in DeepWave, the overview of the design philosophy is that it's a PyTorch-based wave propagation library, and this is designed specifically for FWI. Okay, so there's quite a bit of options for running it for FWI, and its central design decision is to expose the forward modeling operator as a differentiable PyTorch. So it has a computational graph, so that you can actually calculate del J and del M, which is essential to FWI, using some of the PyTorch libraries like the loss that backwards. It backward propagates it. No hand coding up adjoint is required for this case. But then, memory handling in 3D becomes a bit of a problem here. So DeepWave has scalar as well as elastic, and also has scalar bond modeling operations. And the elastic propagator essentially solves in 2D or 3D. You can decide which order and all of that stuff. Yeah, that is totally controlled by user. And you can simply run it on GPU and take advantage of the parallelism. So DeepWave tensors, they live on either CPU or CUDA GPU, depending on what you have. You can give it an option. And the FD kernel is implemented in C++ and CUDA. And this is called from Python via PyTorch extension. Okay. So a single forward call can propagate NS short gathers. You can generate a survey completely for you, and it's limited only by GPU memory. And this shows you a small code snippet as to how you do that. You have to import Torch, which is PyTorch library, and DeepWave. I'll show you in a bit, how you can do that. And then you can generate this model, and this propagator will basically propagate it through this model, and then you can actually give it the source location and all that stuff, and then at the receivers you can grab those wave fields. You can also generate snapshots. And DeVito is one other package, and I think Ashok is now using it as well. So DeVito, it's a domain-specific language, and what do you call, they're calling it just-in-time compiler for finite difference PDE solvers, and that is embedded in Python. So rather than providing pre-built wave propagator, DeVito lets the user define the PDE using SymPy like notations. Okay. And it automatically generates, optimizes, and compiles the corresponding FTC code. So DeVito is is, I would say, more general in the sense that it has a lot more options compared to deep wave right now. And but both are fairly easy to use. The initial hurdle is to build the whole library, and that there are instructions in there you can use. And sometimes you may have to ask your systems person to just help you a little bit with that. And this shows you symbolic PDE specification. You have to import DB2 libraries, define the grid, define your time function, and then define your source function, and then you just define the equation. So this is one equation that basically defines your particular PDE that you are interested in solving, and then you do a stencil, and then this basically does all the calculations that you're interested in. Whoever thought that this would be possible, but now it's almost like just writing the equations and getting the code written by somebody else. So you can use deep wave. These are just my comments. When the primary goal is gradient descent inversion, and you want to experiment with some of the misfit functional, and DeVito when you need maximum computational performance. And I'm not supposed to tell you this, but I won't name the company, but some companies are actually using DeVito-based codes for FWI for production purposes. And so DeVito is very good for using large-scale simulation and inversion because it has a lot of options. You can use it. It has all of these checkpointing and parallelization, OpenMP, MPI, and also if you have GPU version, it runs on GPU. Okay, so you can maintain both of these for tutorial notebooks and things like that. So any question before I move on to the next topic? I
So
want
for
to show.
Bond,
Go ahead.
so for Bond series modeling, do we have any open source options? Deep Wave,
Deep wave has a bond, but that's a different type. It just simply puts the source function on the right hand side of the wave equation. But for bond series, no, but I can give you a simple code for acoustic case.
okay, okay.
I want to basically do something here. Just give me a minute. Okay, are you guys able to see my screen now?
Yes, sir.
Okay, so here I'm showing you a GitHub site where you can find deep wave. Okay, now deep wave it comes with all the instructions, source code, and things like that. It tells you that it provides wave propagation modules for PyTorch uh, and for applications such as seismic imaging, inversion, and so on. So all you have to do is on Unix machines, you can just do pip install, and you can do that. You can also install it on some other. I'm running it on mostly on Unix machines. And here is a nice example of how it. Are you guys able to see the screen, and do you want me to sort of zoom it?
A slight zoom will be better, sir.
Is
Yeah,
this
this
better?
is fine. Yeah.
Okay, so here you are importing torch, then deep wave. So you have to build the deep wave library, and I'll show you some example of running it. And simply using matplotlib from here. So here, this is setting up a velocity model. It's very simple. Like here it is homogeneous 100 by 100, but then filling it up with 1500 meters, and then from 50 on it has 2000. So it's basically a two-layer model. And here you're calling a scalar wave equation solver. It's very simple. So give the velocity model, give the grid spacing, give the delta t. You can define a source wavelet. Here it's a recur wavelet, 25 hertz, 200 samples, 4 millisecond sampling interval, and so on. You have to give it the source location. Here it is 00. Then you have to give it to receiver location, and everything else was default. And then you were basically outputting the snapshot here. So this shows you the velocity model, and this shows you at one receiver location what the wave field looks like, direct wave and the reflected wave here. And this shows you also gradient calculation, which I'm not going to talk about right now. You can ignore that. So I would very strongly recommend that you try to have some experience with this code. Okay. You just have to build the environment and run it. And then if you want to go to DeVito, there is a lot of literature available. It's quite simple to run it. There is a DeVito project. You can just search. Then you can find, especially from the this is how they do it for acoustic, finite domain. This is doing seismic modeling and define the physical problem, acquisition geometry, and all that stuff. Okay. So let me show you a quick run with the deep wave. I don't have the DeVito stuff ready. So I'm just going to show you some of these codes. This is, I'm not sure this is, okay, so this is your deep wave for short calculation. So here, you're basically importing deep wave, matplot libraries, and so on. And the only thing is you have to learn how to use PyTorch, because a lot of these, all of these variables, they have to be converted to torch type. And here I have a Marmusi model. This is 2301 by 751. So you can run this. And see, the first thing it will ask you, press enter to confirm your estimate. Okay. Because I'm actually logged on to my office computer. Oh. Okay. Let me redo this. How many of you guys use VS Code?
Sure, I use it.
Yeah, it's very, very useful.
Yeah.
Okay, so here I have this notebook that I'm using for generating some. This came from DeepWave. So using this for generating Marmusi synthetics. Okay. So here we have. Can you see this, or is it too small? I don't think I can help it much.
Yeah, now it is visible. Yeah.
Okay, so this is your torch library, deep wave, and then from deep wave, I'm importing scalar, which actually does the simulation. And so this is the part where you can say if you have CPU or GPU, you can choose to use either one. The machine that I'm running it on, that I have like 4 GPU cards. So here, this is 2300 751. This is the grid spacing, and this is the part that basically is reading the Marmusi model. And here, I'm generating 115 shots. Okay, so you can make it less. So let's say that I'm generating 10 shots. Okay. And so these are the descriptions of the sources. And this is the receiver description. This is the frequency of the wavelet. This is the number of time samples, sampling interval. And this is the peak time of the wavelet. And then this is your source location. And these are your receiver locations. This is the source amplitude. And now you are here, you're running the scalar. Okay. And then you are getting this. So now I can, this is in one notebook. So I can just run it once and it will basically ask me to go to the Python environment. Okay, so here I have this environment called deep. Okay, so I go there. So then there everything is built in. So it will go there and then pick up whatever basic packages that I need for the library. Now it's supposed to be, once it's done loading it, it will basically start to run. Running doesn't take much time at all. It has oops. I didn't have this problem. Oh, okay, I know what happened. I think it's just some problem with this one. I cannot change it to 10 without changing anything else. So let's run 115 only. It will not take very long. What? Well, I read, oh, CUDA out of memory. Something is going on here, so I cannot run it right now. So we'll have to run it another time. Too bad. But we can, just a second, let me go to this. Okay, any question before we switch to the next topic? I can, are you able to?
Sorry. Yeah, sir, in DeVito, can we implement this elastic as well? I have been running a caustic case.
Okay. Yeah, you can implement it. That's what I was telling you. Some companies are actually using DeVito for elastic FWI.
Yeah, so I have some results on acoustic, but I wanted to test elastic because my aim is to use those products for QI purpose.
Yes, so, definitely. Yeah.
Yeah. So I mean, I wanted to test how this elastic, even for low frequencies, can be used as a starting model for 1D inversion. Let's say Canit or Born series based inversion.
Yeah, definitely. Yeah. That's good. Making good progress.
Yes, sir. Yeah, I mean the results are good. And let me fish it out. I will share you here only. Let me check if I have now.
Yeah. So while we are waiting, is there any comment from the rest of the attendees? Question?
So I will show you some of the problems which I faced first because I'm not able to fish out my final result. But anyway, I will. Can you see my screen, sir, now?
Yeah.
So this was when I could fix the water bottom problem. Earlier, the updates were mostly limited to the water column because it finds the gradient strong over there, so it starts updating water column, and I could
Mm-hmm.
fix it. You can see in the figure at the bottom, which is the change in the velocity.
Yeah,
But when
yeah.
I started with L2 norm, I somehow
Mm-hmm.
could not propagate my updates down below. It was just sitting at the water
Mm-hmm.
bottom, just below the water bottom. Then I
Mm-hmm.
switched to this phase correlation.
Yeah,
Then I
like
could,
I was talking to you
yeah,
other day. Yeah.
yeah. So when I switched to phase, then I could see the updates down below. I'm not able to
Mm-hmm.
fetch it. I will get it and show you, sir.
Mm-hmm. Yeah, this is nice.
Yeah. So this is the update, sir.
Okay,
You can
okay.
see, yeah, you can see the updates now pushing downwards.
Yeah, yeah, yeah.
So this was my first attempt. I
Mm-hmm.
mean, second attempt in the sense that I switched to switched the norms and all those.
Right, right.
And I can see some updates, and we are trying to verify this with the logs as well. And this is
Yeah,
probably the gas sand. We have a well over here.
yeah,
So
yeah.
my next objective is to match this velocity. And in fact, I matched it, but I don't have the screenshot. So
What
this low
about, did you
velocity,
look at
yeah.
the data fit? This Beagle match?
The misfit, sir, with iteration. This is what you mean.
No, I mean, plotting this synthetic
Short
synth.
gathers.
Yeah,
The short gathers. Yeah, I did it. I
mhm.
overlapped the real with the synthetic, and I could
Yeah, yeah.
see the match.
Okay,
There was no cycle skipping on those.
good.
I did it last Thursday. I did it.
So this is the
So
same data that you were showing me earlier.
yeah, in fact, this is the data which you mentioned, GXT
Oh,
lines,
yeah,
10
yeah, yeah.
kilometers.
Wow,
Yeah,
wow. That's nice. Yeah.
so I picked that line. So it's a
Okay,
10
okay.
kilometer offsets, and I could see, I mean, the scale is not proper. Otherwise, there are some updates down below.
So is this
So
data open source or is it somebody has to buy it or something like that?
no, it is not open source, sir. It is closed. I mean, you could approach DGH through some Indian universities, then you might get this data.
Okay. No, I think it
Yeah,
will be
and
nice for some kind of a research work. So,
yeah, sir.
So
We
it
can
may
do it, sir.
available in India DGH actually.
Yeah.
okay.
Or sir, we can collaborate and work on it for
Yeah, I
this,
think
sir.
we should do that. I mean, we can
Yeah.
probably do a paper on that. Elastic is appropriate for this.
Yeah.
So,
So I'm thinking of doing it, sir. Yeah.
so this is from Kerala Konkan Basin or
No,
the
sir.
other
This
side?
is from KG. This is from KG
KG.
Basin.
Okay, okay, okay.
Yeah.
So Kerala
There is-
Konkan side, I think they have some basalts there.
Yeah, there is some basalt. Yeah. But since
Yeah,
our working interest is in KG,
yeah,
so
yeah,
I
yeah,
started with this line,
yeah, yeah.
and there are some hydrates down below. So I'm currently running something down 226 shots down dip.
Okay,
There
okay,
we expect some hydrates. I wanted to
okay,
characterize the hydrates as well.
okay, okay.
So, and the idea is to use this as the starting model for, let's say, Canit-based inversion or bond-based inversion. I don't know how it will work out, but this is the idea. Rather than
Yeah, yeah,
going straight, yeah, rather than going straight to the elastic uh,
yeah.
on this machine, I have only two GPUs, RTX A4000. It is good. I mean, good for 2D
Yeah,
work. It
yeah, yeah,
runs overnight
yeah,
for
yeah.
200 shots. It takes
Okay,
around 12 to 13 hours to run this inversion, a 2D
okay,
acoustic capture device.
okay, okay. Nice.
So, yeah.
Very nice. Yeah, I'm so happy to see this.
Yeah, so it was just because you said that you can do it. So I
Yeah,
started just experimenting with it, and I could do it. Thank you,
yeah.
sir.
The
Thank you for
reason,
your support. Yeah.
oh, no problem. The only reason the correlation based objective function works is because of the amplitude. So the amplitude fidelity is not very strong. So
Yeah. So it is just using the kinematics, right, sir,
yeah,
of the
mostly
events.
kinematics. Yeah, yeah.
Yeah. Yeah. But it is so surprising that just from the kinematics, it could bring such good velocity, which matches the
Yeah,
well.
it'll get the details. Yeah, sure.
So, sir, when do we move to amplitude-based updates? I mean, in elastic case, or this is good enough to use in
I
elastic
think
case as well?
elastic case would be better because in a lot of the elastic effects, are not modeled very well by the acoustic case. And that might actually be. So you can use this velocity model as a starting model for the elastic case, where you can convert this POA velocity to shear wave velocity using some standard equation, like Castagna or something, as a
Yeah,
starting model, and
yeah,
then
okay.
run the inversion and see how it does.
So do we need to smooth it out, or this is good
Yeah,
enough
you need to
to start?
smooth it a little bit. Yeah.
Okay, yeah,
Yeah.
okay, sir.
Okay, so I can do one more lecture. Okay. You guys okay with that? Or you
Santosh,
guys?
you want to continue or you want to continue next week? It's already
Uh,
8:48.
yeah, I think maybe how if it's not if it's a long one, we can take it next week maybe.
Okay, yeah,
If
next
sir
week
is
is
okay
good.
with that. If sir is okay,
Yeah,
well, if you are okay with it, sir.
yeah, that's fine. We can do it next week. Okay.
Yeah, okay, sir.
Okay. Okay.
Okay, sir. Thank you.
Okay.